This video is brought to you by Onshape. Water, the stuff I'm supposed to be drinking but avoid in favor of things that are dramatically reducing my lifespan. I need to go underneath it, and I want a cheaper alternative to a scuba system. Now, cheap usually shouldn't be used in the same sentence as underwater life support systems, but my manager is on vacation, so there's nobody around to make me follow rules. Now, if you follow my channel at all, you may recall that I once built a working two-man submarine and got halfway through building a much smaller, more portable one out of a kayak. Now, the keyword there is portable, and I want something so small that I can just fit it in a car seat or a cabinet or something. See, I have this pool that keeps leaking, and the professionals want me to pay over $1,000 to fix the leak. So I figured if I just had my own air supply, I could get down there myself and patch it up with some hot glue and duct tape. Plus, I live in Florida, so having a way to go underwater is worthwhile. Now, personally, I'm not a big fan of the whole scuba thing. Man was made to walk upright and not to swim around like a fish. I mean, if you think about it, that's kind of going backwards from millions of years of evolution. Hence, in my opinion, the best underwater breathing apparatus is a dive helmet. Basically, the 1800s style approach that's more like an astronaut walking on the moon and less like a human trying to LARP as a fish. The advantage of this setup is that you don't need the ridiculously high pressures that a typical scuba tank has, like 200 to 300 bar or 3000 to 4500 psi. The air supply pressure only has to be equal to or slightly higher than the surrounding water, meaning that just a couple atmospheres of pressure will do. This means you could just use a regular old air tank filled with a common oilless compressor that just goes to around 10 bar or so. The only downside is that a tank like this would have a lot of buoyancy and not really carry that much air compared to a typical scuba tank. But why be burdened by a tank at all? You could just supply the dive helmet directly off an air compressor floating on the surface of the water. Just a couple of caveats though. First off, it has to be an oilless compressor, otherwise you're breathing ultra-fine particles of lubricant oil, and I've heard that lung cancer isn't a very fun way to go. The other caveat is that the compressor needs to be electric. Quite a few divers have died from a negligent setup where a gas-powered compressor was sucking the carbon monoxide fumes from the engine exhaust and delivering it to the diver. This is also not a fun way to go. Finally, the compressor has to deliver enough airflow to actually keep you alive. At an absolute minimum, an average adult human typically needs around 10 liters per minute of fresh air. Although if you factor in elevated breathing rate from physical exertion, that number goes up quite a bit. Also, you're going to need some overhead to compensate for the fact that air is denser as you go deeper. So if, for example, you're breathing 10 liters per minute of air 10 meters underwater where the absolute pressure is 2 atmospheres, the compressor needs to be taking in 20 liters per minute of air on the surface. Now, the nice thing about the whole dive helmet approach is that we don't really have to worry about pesky things like pressure regulators or demand valves like you'd have to worry about with a typical scuba setup. See, an old-fashioned style diving helmet is literally just a miniature diving bell that you stick your head inside of. Think bucket turned upside down in the water. Same thing. Whether your air supply pressure is 1,000 atmospheres or just a few atmospheres, it's going to expand to equal the outside water pressure because the bottom of the helmet is open. So as the air expands, it pushes down the water line inside the helmet, and any excess air overflows as bubbles. Now, if there's bubbles all over the helmet, visibility is going to be really bad, so typically there's a designated port for the excess air to leave. If there's an air exit a little above the bottom, all the excess air will go out through there instead of the very bottom edge of the helmet. This way, we can make sure the bubbles stay where we want them, so in the back of the helmet where they don't obstruct the view. For even more bubble management, the air exit can be connected to a pipe that runs up above the top of the helmet, so the bubbles will always come out above the helmet and not obstruct the view even if the air exit is at the front, sort of like a reverse snorkel. As for the air supply, it's pretty straightforward. You've just got a compressor and a battery. Well, in theory it's that simple, but the only snag here is that most compressors that run off DC power, like 12 or 24 volts, are pretty tiny units that are made for light-duty applications like inflating car tires, and they don't have the required airflow rate to keep a person breathing safely. There might be some specialized DC ones that have a much higher flow rate, but usually you're paying an unreasonable amount of money for them. So the more realistic approach seems to be just using an air compressor meant to run off mains power and feeding it from a 12 or 24 volt battery by way of an inverter. The motors in these things usually aren't too sensitive about the waveform being a pure sine wave, so you don't need to spend huge amounts of money on a fancy pure sine wave inverter, just something good enough to be reliable. As an additional safety measure, we're probably going to want a few minutes of reserve air in case the compressor craps out. Typical shop air compressors already have a decent sized tank attached, so now that I think about it, I guess I could just get my shop compressor and hook it up to an inverter and stick it on a floaty. Based on the specs, it looks like it should work. Extrapolating these numbers backwards to 15 psi or 1 atmosphere, that's 1.45 CFM, or about 41 liters per minute. That would be at a depth of about 10 meters or 33 feet, and I definitely do not want to try going any deeper than that with a homemade helmet. Besides, most dive sites around Florida are pretty shallow, so there's going to be plenty to see within that depth limit, assuming this thing actually works. Okay, so that's a good starting point for the air supply. Now, what about the helmet itself? Well, first off, I'm going to need to figure out the size of the thing, and the average numbers online probably won't be helpful due to my excessively large Jimmy Neutron-shaped head. Most of that is from water, by the way, not brain mass. So the quickest way to do that was just to hot glue together some bits of cardboard and see what constituted a reasonable fit. This didn't have to be a perfect replica, just a sort of bounding box to figure out the minimum outer dimensions. This, in addition to a couple of holes cut in the front and sides, would give me a good idea of the field of view, and I'd say that's probably enough information I need to proceed with the CAD design. The box size I came up with was 7.5 inches wide, 9.75 inches deep, and 11.25 inches high. And here's all those dimensions in metric. That comes out to 823 cubic inches, or 13.5 liters of water displacement in an absolute worst case. All of this displaced water is going to need ballast to force the helmet to sink, or at very least be neutrally buoyant. Of course, there's going to be some relatively large corner radii, so that'll reduce the water displacement somewhat, and the introduction of the noggin into the inside of the helmet will also reduce the amount of ballast that'll be needed, since a human head is pretty similar density to water. I don't have a way to weigh my head, but I found online that the average adult head weighs about 11 pounds or 5 kilos, so subtracting that from the approximate water displacement of the helmet, I probably have around 15 pounds or just under 7 kilos of buoyancy that'll need to be negated. Now, ordinarily this was taken care of by having the whole thing made out of some really thick-walled dense metal like steel or copper or brass, but ABS plastic isn't going to sink too well in water, so the helmet is going to need some external weights to get it to sink. Having something rigidly attached is really going to limit my range of motion if I look up or down, so my idea was to have two plates that are hinged on the front and back of the helmet, which can then have steel barbells bolted to them until there's enough weight to sink. Kind of feels like designing a medieval suit of armor. Next, we need a place for the air inlet and outlet. As I discussed earlier, the outlet will be on the bottom of the helmet on the back side, but for the inlet, we've got a couple different options. In some of the older examples of dive helmets, the air inlet is at the very top of the helmet. This is probably the simplest approach, but if for whatever reason the compressor on the surface loses pressure, it basically becomes a suction port. In a mild case, this could cause an uncomfortable situation where your head acts as a plug on the inlet opening, or in an extreme case, if you were super deep down, you could end up like one of those meme videos about Delta P. This is pretty simple to negate with a check valve, and I don't ever plan to go beyond 10 meters down, meaning there's never going to be more than an atmosphere of vacuum on the inlet during a supply failure, so I'm just going to go ahead and put the valve and inlet on the top of the helmet. Okay, let's start designing the model for this thing. For this project, I'm going to be using Onshape to do the CAD design, because I'm curious about this newfangled idea of cloud-based CAD software. See, even if your PC is effectively just a potato with some USB ports, you can still do really detailed, memory-intensive CAD work because all the heavy lifting of graphic rendering is outsourced to one of those giant warehouses full of RAM sticks. You know, the same sort of facilities being used to generate the conversation outputs for your AI girlfriend. Onshape works on Windows, Mac, and Linux, so you could literally have a Raspberry Pi running off a potato battery and still make complex CAD assemblies. In fact, it even works on Android and iOS, so you could do everything on your phone. Why you'd want to do that, I have no idea, but by God, you've got the option. There's no headaches with software installation or updates, and it never crashes, so you don't have to worry about data loss or file corruption. It has an undo capability all the way back to square one, and because Onshape is cloud-based, it allows multiple people to collaborate on one design in real time. It's also got finite element analysis and CAM features, and if you're a hobbyist, there's a free version available that has most of the features of the professional version. They've even navigated the quagmire of US federal government red tape and have an Onshape government version which is usable for companies that have to be compliant with programs like ITAR or EAR. There's a ton of other features that I haven't mentioned, and I've only spent a couple hours playing with it so far, but this seems like a solid software package. I was pretty skeptical of the whole cloud-based idea going into it, but I've actually really enjoyed using it, and I could definitely see myself using it for future projects. If you want to try the professional version of Onshape, you can get 6 months for free using their discovery program by clicking the link in the description. Being able to do CAD work in my web browser from any computer anywhere has made my life way easier, so I'm giving this my official seal of approval. Now go sign up. Okay, so here's what I've got. There's a basic bucket to go over the head with 3 6-inch or 10 centimeter diameter windows, an inlet port, hinges for ballast weights, and an outlet port at the back. The socket for the outlet port is designed to connect to a 3/4 inch PVC pipe, which will be the air overflow tube and run up to the top of the helmet. This flat area will be for a strap to secure the pipe. The flat area on the top of the helmet will be for mounting a carry handle, and the flat area slightly off to the side is a placeholder for mounting the other hardware in the future, like a light or a camera. The window ports are slightly undersized so that the windows can push against the inside walls of the helmet. Intuition might have you thinking that the water would be pushing the windows inward, but it's actually the opposite. Because the pressure on the inside of the whole helmet is equal to the water pressure at the very lowest point where the air exits, the outside water pressure on the windows will actually be slightly lower than that because they're at a slightly shallower depth, so there will actually be a small amount of outward pressure acting on them. The maximum build area for my printer is 250 by 210 millimeters, so obviously the whole helmet isn't going to print in one piece. Instead, it'll be divided up into 4 separate pieces. These will initially be joined just by gluing, but then they'll be reinforced with fiberglass and epoxy to make the joints structurally sound. The print times for the first 2 pieces were excessively long because I didn't realize I had my slicer set to 0.1 millimeter instead of 0.2 that I usually print at. So there's the first piece, and it looks pretty clean and free of defects. After a couple more days of printing, the other 3 came out, and then I carefully glued them all together and did a test fit. No unexpected surprises, and everything seems to mesh together pretty nice. Next, I used some fiberglass strips and epoxy to reinforce the joint, since it would be really bad if this thing came apart underwater. It's important to use epoxy and not polyester resin on ABS because the polyester resin will dissolve ABS. Then I fill the gaps and print lines with a thin coat of Bondo, sand everything down, and apply a coat of epoxy to get a little bit of a sheen and seal the Bondo against the water. Then the air outlet pipe is installed on the backside, also using epoxy, and the whole thing is lightly sanded and then given a yellow coat of paint. Once the paint dries, I finish it off with some polyurethane spray, then mount the inlet valve, the carry handle, and the strap to hold the outlet pipe in place. The bolts are inserted with a generous application of silicone caulk to keep them from leaking water. The very last thing I do is install the windows, which just consist of applying clear silicone caulk and pressing them in place. The window frames keep them from moving side to side, and the pressure will be pushing them outward, so for the moment I don't think there's a need to bolt them in. So there's the completed helmet. It's a little claustrophobic, but seems to be a reasonably good fit otherwise. The only thing left to do is add the ballast weights and the helmet will be done. The plates that hinge to the helmet are basically just there to give the weights something to attach to and keep them from rubbing uncomfortably against my skin. They're just 3D printed panels with a sheet of neoprene rubber on the sides facing me and a hole in the middle for mounting the weights with a large bolt. The hinge arms are separate pieces that are screwed to the plates. The reason for this was to allow me to 3D print them in the direction with the strongest possible grain. Alright, we got the weights hinged on the helmet, now let's do a quick float test. As you can see, there's still a little bit of positive buoyancy, but once my head is inside, it should be negatively buoyant. So now I'm going to do a quick underwater test just running the compressor off the mains by the side of the pool. So as you can see, I'm holding the helmet quite a bit because it tends to want to drift off my head a little whenever I exhale and increase the volume of air inside. Also, my buoyancy is so close to neutral that it makes it pretty much impossible to walk underwater, so I kind of just have to bounce around on my butt. So I added an additional 5 pounds of barbells on either side for a total of 10, which should fix the issue. Let's try it now. Okay, much better. It's still pretty awkward to try to walk, but at least the helmet stays seated on my head and I don't have to hold it down all the time. One thing I found really irritating was that the overflow air doesn't seem to flow continuously, but rather flows out in bursts every second or two, which are pretty loud inside the helmet, so I'll have to redesign the air outflow. On the positive side, there doesn't really seem to be much fogging on the windows, which was my biggest concern. My guess is that there's so much new air flowing in that the humidity doesn't have a time to build up from the water at the bottom, so it stays pretty close to surface humidity. It also means the air inside doesn't have a chance to get hot, which contributes a lot to fogging. Okay, the helmet works, so at least the first half of this project is a success. Now it's time to move on to the air supply. I did another longer test in the pool with the air compressor running off mains to ensure it would provide enough airflow and I wouldn't get dizzy or black out. And after 10 minutes of doing that, I felt totally fine, so I know it's at least providing enough airflow. Now I need to get it to run off a 12-volt battery. With approximately 15 to 20 psi of load, it seems to pull about 280 watts of power, and I've got a small inverter that's capable of 400 watts, but I'm not sure how much I trust it. So to be safe, I'm going to run it off this much bigger 2000 watt inverter, which is way overkill, but from a reliability standpoint, it's probably good to have it running way below its rated load if it's going to be at 100% duty cycle. For the battery, I've already got a pair of 35 amp hour 12 volt lead acid batteries on my remote controlled lawnmower, so I guess I'll just go ahead and borrow one of those. Now, assuming the inverter is 100% efficient, which it obviously isn't, this thing would need to supply about 23 amps, so around 0.65 C, which lead acid batteries don't really like to do. Ideally, a LiPo or a LiFePO 4 battery should be used in an application like this, but I already had the lead acid, so that's what I'm going to use. Everything is wired up, and when I switch it on, we're getting air. Trying the dive helmet once again with the air supply sitting on dry land, everything seemed to work the same as before. I've got a working battery-powered air supply, so the second half of the system is almost complete. The final piece of the system is the flotation for the air supply. I've got a couple of pool floaties already, and I once saw a pretty fat kid floating in this big one without a problem, so I guess I'll use that one for my supply. To mount the hardware, I just cut a round plywood panel to go over the top of the floaty and secured it by tying it down through these holes. To save weight, I could have cut out a lot of material in the middle, but I don't want water to splash up into the inverter or compressor, so having the solid deck helps that. The inverter is mounted at the highest point since it's the most sensitive to water, and I added a diver down flag in case I decide to take this out into open water. Well, it doesn't sink, and it appears to be pretty stable, so I think we've got a usable floating air supply. The supply hose is just a conventional shop hose with the exception of the ends, which are fittings for 1/4 inch flares. These are the same fittings you'd use to connect to a refrigeration system. I like these because they're quick to connect or disconnect, but they don't leak like the quick connect fittings used for air tools. Alright, time to run the entire system with everything in the water. Let's try it out in the dark. Here I was trying to put together some Legos, but they just wanted to float away from me. I also got the camera pointed a little too far down. Alright, so this worked pretty well, although I'd really like a deeper body of water to try it in. Eventually I'm going to try taking it to the Atlantic, but at the moment the water is really cold and the waves can get pretty choppy, so it's not a good idea. Some inland site like Crystal Springs on the northwest side of Florida might be a better option if I can find the time to make the drive since it's several hours away from me. Anyway, that's how I built a 3D printed diving helmet. If you want to try it yourself, I've included the STL files in the description, although I wouldn't recommend it unless you really know what you're doing, because anything underwater has the potential to be pretty dangerous, even in shallow water. But it worked well enough that I think it'll be useful for some other underwater project ideas I've got, so I'll probably be using it in a future video at some point. Thanks again to Onshape for sponsoring this video. Okay, bye.